Hello there, and welcome to another gentle journey through the mysteries of science. I'm so glad you found your way here tonight. Perhaps you've had a long day filled with moments that felt too fast or too slow, or maybe you're simply curious about the nature of time itself. Either way, you're in the right place to let your mind drift peacefully through one of the most fascinating concepts in all of physics. Tonight, we'll explore the quiet science of time travel. Not the dramatic stories of movies and books, but the real physics that whispers softly about how time bends, flows, and dances through the universe. You have nothing to do but rest. Let your breathing slow, your muscles relax, and your thoughts settle like leaves on still water. Because tonight, we're not rushing anywhere. We're simply floating through the gentle currents of temporal possibility. Time moves differently everywhere you go. On mountaintops and in valleys, near massive objects and in empty space, time itself stretches and compresses like a slow, cosmic breath. We'll discover how every step you take is a tiny journey through time, how gravity whispers to clocks, and how the universe itself might hold pathways to yesterday and tomorrow. If these peaceful explorations help you unwind or offer you a quiet way to drift into sleep, consider supporting the channel. It helps others find their way to these calm, curious moments too. Now let your mind grow light and your body settle deeper. Let's begin our gentle drift through time. The gentle physics of time's flow. Time is not the steady river we imagine it to be. It flows like honey in some places, rushes like rapids in others, and sometimes pools in quiet eddies where moments stretch long and peaceful. Einstein discovered this more than a century ago, and his gentle equations still guide us through time's mysteries. The very fabric of reality bends and curves around mass and energy, creating a universe where time itself becomes as malleable as clay in the hands of a cosmic sculptor. Every clock in the universe runs at its own pace. The clock on your nightstand ticks differently than one on the International Space Station, not by much, but enough that scientists must adjust for it. Time moves more slowly where gravity is stronger, more quickly where it's weaker. This is called time dilation, and it happens everywhere all the time in ways so subtle we barely notice. The gravitational field of Earth itself acts as a temporal modifier, stretching and compressing the moments of our lives in ways that would have seemed impossible to physicists just over a century ago. When you climb a flight of stairs, you age slightly faster than someone remaining on the ground floor. The difference is unimaginably small, measured in billionths of seconds, but it's real. Your head ages faster than your feet throughout your entire life, though the difference would take precision instruments to detect. This extraordinary fact reveals the intimate connection between space, time, and gravity that Einstein first described in his theory of general relativity. Every step upward carries you into a slightly weaker gravitational field, where time moves just a fraction faster than it does closer to Earth's center. The mathematics underlying this phenomenon are elegant in their simplicity, yet profound in their implications. Einstein's field equations describe how matter and energy curve space-time, and this curvature is what we experience as gravity. But the curvature affects not just the paths objects take through space, but also the rate at which time passes. The stronger the gravitational field, the more severely space-time is curved, and the more dramatically time is slowed relative to regions of weaker gravity. This means that time passes more slowly at sea level than on a mountaintop, more slowly on Earth than in the vacuum of space, and more slowly near massive objects like stars than in the empty regions between galaxies. The implications extend far beyond abstract physics. Every massive object in the universe creates its own temporal landscape, a topography of time where moments stretch and compress according to the local strength of gravity. Near the surface of the Sun, time moves noticeably slower than it does here on Earth. Near a neutron star, with its incredibly dense matter packed into a sphere only kilometers across, time would crawl compared to our terrestrial experience. And near a black hole, where gravity becomes so strong that not even light can escape, time dilation reaches extreme proportions that challenge our everyday understanding of temporal flow. But it's not just gravity that affects time's passage. Motion also plays a crucial role in determining how quickly or slowly time flows. According to Einstein's special theory of relativity, time moves more slowly for objects in motion relative to stationary observers. The faster an object moves through space, the more slowly it moves through time. This reciprocal relationship between spatial velocity and temporal velocity reveals the deep unity of space and time, fused together into the four-dimensional fabric of space-time that underlies all physical reality. The universe thus presents us with a rich tapestry of temporal variation. High-speed particles racing through cosmic ray showers experience time differently than the atoms in the rocks beneath our feet. Satellites orbiting Earth at thousands of miles per hour age more slowly than their ground-based counterparts. Even the rotation of our planet creates subtle variations in the flow of time, with objects at the equator moving faster through space and therefore aging slightly more slowly than those at the poles. These effects combine in complex ways throughout the cosmos. A satellite in orbit experiences both the time dilation due to its high orbital velocity and the time acceleration due to its position in Earth's weaker gravitational field high above the surface. The two effects partially cancel each other, but don't exactly balance, requiring precise calculations to predict the net temporal shift. This interplay between gravitational and velocity-based time dilation creates an intricate choreography of temporal variation that plays out across every scale of the universe. The discovery of time's flexibility fundamentally changed our understanding of reality itself. Newton's clockwork universe, with its absolute time ticking away uniformly everywhere, gave way to Einstein's relativistic cosmos, where time becomes as relative as position or velocity. This shift in perspective opened new realms of possibility and wonder, revealing a universe far stranger and more beautiful than previous generations could have imagined. Time became not just the stage on which physical events unfold, but an active participant in the cosmic drama, bending and flowing according to the distribution of matter and energy throughout space. Time dilation in every day. Life GPS satellites orbiting Earth experience time about 38 microseconds faster each day than we do on the surface. Without accounting for this time dilation, GPS would become inaccurate by about 6 miles per day. The satellite's clocks must be adjusted constantly to keep your navigation working properly. This practical application of Einstein's theories demonstrates how the abstract concepts of relativity have become essential to modern technology. Every time you use your phone to navigate to a restaurant or find your way home, you're relying on corrections for both gravitational and velocity-based time dilation, calculated with extraordinary precision. The GPS system consists of a constellation of satellites orbiting approximately 12,500 miles above Earth's surface, moving at speeds of about 8,700 miles per hour. At this altitude, Earth's gravitational field is weaker than it is at the surface, causing the satellite clocks to run faster by about 45 microseconds per day due to gravitational time dilation. However, the high orbital velocity of the satellites causes their clocks to run slower by about 7 microseconds per day due to velocity-based time dilation. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground-based clocks. This seemingly tiny discrepancy would accumulate rapidly if left uncorrected. GPS works by measuring the time it takes radio signals to travel from satellites to receivers on Earth's surface. Since radio waves travel at the speed of light, precise timing is crucial for accurate distance measurements. A timing error of 38 microseconds would translate to a distance error of about 11 kilometers, making GPS virtually useless for navigation. To prevent this, the satellite clocks are deliberately set to run slower before launch, compensating for the relativistic effects they'll experience in orbit. Particle accelerators routinely observe time dilation in even more dramatic fashion. Subatomic particles that normally decay in microseconds can live thousands of times longer when accelerated to near light speed. Time literally slows down for these tiny travelers, stretching their brief lives into longer, more leisurely journeys. Ferns, for example, are unstable particles created when cosmic rays strike Earth's atmosphere. Under normal circumstances, muons decay so quickly that they shouldn't survive the journey from the upper atmosphere to Earth's surface. Yet detectors on the ground regularly detect muons created high in the atmosphere, their lives extended by time dilation as they race downward at nearly the speed of light. This phenomenon allows physicists to study short-lived particles that would otherwise be impossible to observe. By accelerating particles to extreme velocities in particle accelerators, like the Large Hadron Collider, researchers can stretch the lifetimes of unstable particles, giving them enough time to travel measurable distances and interact with detection equipment. The particles themselves experience normal lifetimes from their own reference frame, but from the laboratory's perspective, they appear to live much longer than they should according to their known decay rates. Even commercial airliners experience measurable time dilation, though the effects are much smaller than those seen in particle accelerators or GPS satellites. Passengers on eastbound flights age slightly less than those on westbound flights due to the rotation of Earth and their relative velocities. The difference is infinitesimal, measured in nanoseconds for typical flight durations, but atomic clocks can detect it with remarkable precision. When a passenger flies eastbound, they're moving in the same direction as Earth's rotation, increasing their total velocity relative to a non-rotating reference frame. This additional velocity causes time to pass slightly more slowly for them, compared to someone on the ground. The famous Half-Keating experiment in 1971 demonstrated this effect by flying atomic clocks around the world on commercial airliners. The eastbound clocks lost time relative to a reference clock on the ground, while westbound clocks gained time, exactly as predicted by relativity theory. The experiment provided compelling evidence for time dilation in everyday circumstances, and showed that even routine human activities, like air travel, involve measurable relativistic effects. These everyday examples of time dilation reveal how deeply relativity is woven into the fabric of modern life. From the smartphone in your pocket to the particles created by cosmic rays striking the atmosphere above, relativistic effects surround us constantly. They remind us that time is not the absolute, unchanging backdrop that intuition suggests, but rather a dynamic aspect of reality that responds to motion and gravity in precise, predictable ways. Every moment of our lives unfolds against this relativistic stage, where time flows like a river, with currents that vary from place to place and moment to moment, creating the rich temporal landscape in which all physical processes play out. The twin paradox, a gentle thought experiment. One of the most peaceful thought experiments in physics involves two twins. One stays on Earth, while the other travels to a distant star at nearly the speed of light. When the traveling twin returns, they will have aged less than their Earth-bound sibling. This isn't science fiction, it's a consequence of special relativity. The traveling twin experiences time more slowly during their high-speed journey. What feels like a few years to them might be decades to their twin on Earth. They return to find a changed world, having essentially traveled into their own future through the simple act of moving very, very fast. This gentle paradox reveals one of the most profound insights about the nature of reality. Time is not universal. Each observer carries their own personal clock, their own measure of duration, and these clocks can drift apart in the most dramatic ways imaginable. The twin who ventures into space doesn't experience anything unusual from their own perspective. Their heartbeat remains steady, their thoughts flow at their normal pace, and if they could look in a mirror, they would see themselves aging at what feels like the normal rate. Yet relative to their earthbound sibling, they are moving through time like a swimmer, moving slowly through thick honey. The mathematics underlying this phenomenon are surprisingly straightforward, emerging from Einstein's special theory of relativity. As objects approach the speed of light, time dilation becomes increasingly pronounced. At 90% of light speed, time would pass about 2.3 times more slowly for the traveler. At 99% of light speed, the factor increases to about 7 times. At 99.9%, time would crawl along at roughly 22 times slower than normal. The closer to light speed the traveler moves, the more extreme the time dilation becomes, approaching infinity as the velocity approaches the ultimate cosmic speed limit. This isn't just theory. Experiments with atomic clocks flown around the world have confirmed this effect. Time really does slow down for objects in motion relative to stationary observers. The Half-Keating experiment of 1971 demonstrated this beautifully, showing that clocks flown eastward around the Earth lost time, while those flown westward gained time, exactly as relativity predicted. More recent experiments with particles in accelerators have shown time dilation effects so extreme that particles with lifetimes measured in microseconds can survive, for what would normally be millions of times, longer than possible. But the twin paradox presents a puzzle that has intrigued physicists for over a century. If motion is relative, why doesn't the earthbound twin also experience time dilation from the perspective of the traveling twin. Shouldn't each twin see the other's clock running slowly? The resolution lies in the fact that the situation is not perfectly symmetric. The traveling twin must accelerate to leave Earth, decelerate upon reaching their destination, accelerate again to begin the return journey, and finally decelerate upon arriving back on Earth. These periods of acceleration break the symmetry and are what ultimately determine which twin ages less. During the acceleration phases, the traveling twin briefly experiences effects similar to those in a gravitational field. According to Einstein's principle of equivalence, this principle states that acceleration and gravity are indistinguishable from each other in their effects on space-time. The periods of acceleration experienced by the traveling twin introduce additional complexities to the time dilation calculation, but they don't change the fundamental conclusion. The twin who travels at high speed will return younger than the one who remained on Earth. The implications of this thought experiment extend far beyond abstract physics. It suggests that time travel to the future is not only possible but inevitable for anyone who travels at high speeds. The traveling twin has literally journeyed into what was once their future, experiencing firsthand a world that has aged decades while they have aged only years. They become visitors to their own tomorrow, witnesses to the passage of time from a perspective that few could ever imagine. This form of time travel is one-way and irreversible. The traveling twin cannot return to their original time any more than we can travel backward through our own past. They have traded their present for a future they could never have experienced otherwise, gaining years of life by losing decades of shared time with their loved ones. It's a poignant reminder that even the most beautiful physics can carry profound human consequences. The twin paradox also illustrates the fundamental unity of space and time. The faster an object moves through space, the more slowly it moves through time, as if the universe maintains a constant total velocity through the four-dimensional fabric of space-time. This relationship suggests that space and time are not separate entities, but different aspects of a single, unified reality that Einstein called space-time. Gravitational time dilation, how mass bends. Time gravity doesn't just pull objects toward each other, it pulls on time itself. The stronger the gravitational field, the slower time moves. This means time passes more slowly at sea level than on a mountaintop, more slowly on Earth than in space, more slowly near the Sun than near Pluto. Near a black hole, this effect becomes extreme. If you could hover just outside a black hole's event horizon, watching a friend fall in, you would see their movements gradually slow down until they appeared frozen in time. From your perspective, they would seem suspended at the edge, never quite falling in. But from the falling person's perspective, time would feel normal. They would cross the event horizon in what seems like a reasonable amount of time, unaware that to outside observers, they appear to be moving through temporal molasses. This gravitational influence on time represents one of Einstein's most profound insights about the nature of reality. Mass and energy don't just curve space. They curve time as well, creating a four-dimensional landscape of space-time, where both spatial distances and temporal intervals are stretched and compressed according to the distribution of matter and energy. Every massive object in the universe sits at the bottom of a gravitational well that affects not just the motion of other objects, but the very flow of time itself. The effect is subtle in everyday life, but becomes increasingly dramatic as a gravitational fields strengthen on Earth's surface. Time runs about 22 microseconds per year slower than it would in the absence of Earth's gravity. This tiny difference accumulates over geological timescales, meaning that the center of the Earth has aged about 1.5 years less than its surface over the planet's 4.5 billion year history. Your feet, being slightly closer to Earth's center, age infinitesimally more slowly than your head, though the difference is far too small to measure with any conceivable biological process. The sun's much stronger gravitational field creates more noticeable effects. Time at the sun's surface runs about 2 parts in a million, slower than it does here on Earth. For a photon struggling to escape the sun's gravitational well, this time dilation manifests as a redshift in its light, stretching its wavelength as it climbs out of the gravitational field. This gravitational redshift has been measured with exquisite precision and provides one of the most direct confirmations of Einstein's predictions about how gravity affects time. But It's near neutron stars and black holes that gravitational time dilation reveals its most spectacular effects. A neutron star, with matter so dense that a teaspoon would weigh as much as a mountain, creates gravitational fields so intense that time at its surface runs significantly slower than it does in the space around it. Near a black hole, these effects become extreme beyond imagination. The event horizon represents the boundary, where gravitational time dilation becomes infinite from the perspective of distant observers. This creates one of the most haunting scenarios in all of physics. If you were to watch someone fall into a black hole, you would never actually see them cross the event horizon. Instead, you would see them slow down as they approach, their image becoming increasingly redshifted and dim until it fades from view. From your perspective, they would appear frozen at the edge of the black hole, suspended forever in a moment of time that never quite reaches its conclusion. The falling person's watch would appear to tick more and more slowly until it seems to stop entirely. Yet from the perspective of the person falling into the black hole, their experience would be entirely different. They would feel time passing normally, would see their watch ticking at its usual rate, and would cross the event horizon in what seems like a finite, reasonable amount of time. The extreme time dilation that makes them appear frozen to distant observers would be completely imperceptible from their own reference frame. They would experience the passage through the event horizon as a normal event in their personal timeline, unaware that to the outside universe, they have become temporally isolated. This asymmetry between different observers' experiences reveals the deeply relational nature of time in Einstein's universe. There is no single universal clock that all observers can agree upon. Instead, each observer carries their own measure of time, and these measurements can diverge in the most dramatic ways depending on their motion and their position in gravitational fields. Time becomes not an absolute backdrop against which events unfold, but an integral part of the dynamic, curved space-time that constitutes physical reality. The practical implications of gravitational time dilation extend into many areas of modern technology. GPS satellites, orbiting in Earth's weaker gravitational field, experience time running faster than it does on the surface, requiring constant adjustments to maintain accuracy. Atomic clocks used in precision timekeeping must account for their altitude above sea level. Even the operation of particle accelerators must consider relativistic effects as particles gain energy and experience time dilation. These effects remind us that we live in a universe far stranger and more wonderful than everyday experience suggests. Every massive object around us is constantly modifying the flow of time, creating invisible temporal currents that ebb and flow according to the distribution of matter and energy throughout space. We move through this temporal landscape as naturally as fish swimming through water, largely unaware of the subtle variations in time's passage that surround us at every moment. Closed time-like curves paths through space-time. Einstein's equations permit something called closed time-like curves, paths through space-time that loop back to their own past. These aren't science fiction inventions, but mathematical solutions to real physics equations. They represent possible routes through the fabric of reality itself. These curves could theoretically allow travel to the past, though whether they actually exist in nature remains an open question. The universe seems to have mechanisms that prevent paradoxes, suggesting that even if such paths exist, they may be self-consistently regulated by physics itself. The concept of closed time-like curves emerges from the mathematical framework of general relativity, where space-time is treated as a four-dimensional manifold that can be curved and twisted in extraordinary ways. In this geometric picture of the universe, what we normally think of as straight lines through time become curves that can bend back upon themselves, creating loops in the temporal dimension, just as surely as a path through space might curve back to its starting point. These aren't violations of Einstein's equations, but rather exotic solutions that push the mathematical formalism to its most extreme conclusions. To understand how such curves might form, consider that in Einstein's universe, matter and energy don't just curve space but curve time as well. When massive objects rotate, they drag space-time along with them in a phenomenon called frame dragging. This effect is subtle around Earth or the Sun, but becomes pronounced near extremely dense, rapidly rotating objects. In such environments, the fabric of space-time itself begins to swirl and twist, potentially creating pathways where a traveler could journey forward through space while moving backward through time. eventually arriving at their own past. Some solutions involve rotating black holes, called Kerr black holes, which might contain closed time-like curves in their inner regions. Within the ergosphere of a rotating black hole, space-time is dragged around so violently that the normal relationship between space and time becomes severely distorted. In the inner region, between the outer and inner event horizons, the mathematics suggests that time-like geodesics could exist that loop back to their own past. A traveler following such a path would experience time moving forward from their own perspective while actually journeying into their own history from the viewpoint of distant observers. The implications are staggering and troubling in equal measure. If closed time-like curves exist, they would seem to permit violations of causality, the fundamental principle that causes must precede their effects. A traveler could theoretically journey back to prevent their own birth, create information out of nothing, or generate paradoxes that seem to tear at the logical foundation of physical law. Yet the mathematics of general relativity treats these possibilities with the same stern objectivity it applies to more familiar phenomena like planetary orbits or the bending of light around massive objects. Others involve exotic matter with negative energy density, materials that may or may not exist in reality. Such matter would have the peculiar property of creating repulsive gravitational effects, pushing rather than pulling on nearby objects. The stress-energy tensor describing this exotic matter would violate what physicists call energy conditions, mathematical statements that seem to be satisfied by all known forms of matter and energy. Whether such exotic matter can exist remains one of the deepest puzzles in theoretical physics, touching on fundamental questions about the nature of energy and the limitations imposed by quantum mechanics. The study of closed time-like curves has led physicists to propose various chronology protection mechanisms that might prevent paradoxes from occurring. Stephen Hawking suggested that quantum effects might conspire to destroy any closed time-like curve just as it begins to form, preventing time travel to the past through a kind of cosmic censorship. The idea is that virtual particles and quantum fluctuations would build up to infinite densities along any potential closed time-like curve, creating a feedback loop that would destroy the curve before it could be traversed. More recently, physicists have explored the possibility that closed time-like curves might be self-consistently regulated through what's called the Novikov self-consistency principle. This idea suggests that if travel to the past is possible, the laws of physics would ensure that only self-consistent histories can occur. A time traveler would find themselves unable to create paradoxes, not through any external constraint, but because the very structure of space-time would guide events toward consistency. They might attempt to prevent their own birth, but would inevitably fail, perhaps through a series of unlikely but not impossible coincidences that preserve the timeline they came from. The mathematics describing closed time-like curves also reveals deep connections between general relativity and thermodynamics. The second law of thermodynamics, which states that entropy always increases, provides time with its arrow, its preferred direction from past to future. In regions of space-time containing closed time-like curves, this arrow becomes ambiguous or even reversed, leading to scenarios where heat could flow from cold objects to hot ones or where broken vases could spontaneously reassemble themselves. These exotic solutions to Einstein's equations serve as powerful tools for exploring the logical boundaries of our physical theories. They force us to confront fundamental questions about the nature of time, causality, and the relationship between mathematics and physical reality. While no closed time-like curves have been observed in nature, and many physicists suspect that unknown physical principles prevent their formation, their theoretical existence continues to illuminate the strange and wonderful landscape of possibilities that emerges from our best understanding of space, time, and gravity. Wormholes. Tunnels through space and time. Wormholes are theoretical passages through space-time that could connect distant regions of the universe or even different times. Think of them as cosmic shortcuts, tunnels bored through the very fabric of reality. While they emerge naturally from Einstein's equations, their existence remains purely speculative. If wormholes exist, they would likely be incredibly unstable, collapsing almost instantly unless held open by exotic matter with bizarre properties. This hypothetical matter would need negative energy density, something that might violate the known laws of physics. The mathematical description of wormholes begins with the Einstein-Rosen bridge, a solution to Einstein's field equations discovered in 1935. This solution describes a tunnel-like connection between two separate regions of space-time, potentially linking distant parts of our universe, or even connecting our universe to entirely separate universes. The geometry resembles a tube or tunnel, with two mouths connected by a throat of minimal cross-sectional area. Travelers entering one mouth could, in principle, emerge from the other mouth, having traversed a path through space-time that bypasses the normal three-dimensional route between the two locations. The most familiar analogy for understanding wormhole geometry involves imagining a two-dimensional ant walking on the surface of a folded piece of paper. If the ant wants to travel from one side of the fold to the other, it would normally have to crawl along the surface of the paper, covering a considerable distance. But if there were a hole punched through both layers of the folded paper, the ant could take a shortcut through the hole, dramatically reducing the distance of its journey. Wormholes would function similarly in the four-dimensional space-time of our universe, providing shortcuts through higher dimensional space that could connect regions separated by vast distances or even different periods of time. Even if stable wormholes could exist, traveling through them would present enormous challenges. The gravitational forces near the entrance might tear any traveler apart long before they could enter the tunnel itself. The throat of a wormhole would be a region of extreme space-time curvature, where tidal forces could stretch and compress matter in ways that would be lethal to any known form of life. The gravitational gradient across even a modest-sized object would be so severe that different parts of the object would experience vastly different accelerations, literally pulling it apart at the molecular level. The instability of wormholes presents perhaps the greatest obstacle to their practical use. According to general relativity, any wormhole that forms naturally would collapse so quickly that not even light could traverse it before the throat pinches closed. The collapse would be driven by the wormhole's own gravitational field, which would cause the throat to contract at nearly the speed of light. To keep a wormhole open long enough for matter or information to pass through, it would require the presence of exotic matter with negative energy density throughout the throat region. This exotic matter would need to violate the null energy condition, a mathematical statement that says the density of energy, as measured by any light ray, cannot be negative. All known forms of matter and energy satisfy this condition, including dark matter and dark energy. The hypothetical exotic matter needed to stabilize wormholes would have properties unlike anything ever observed in nature, creating repulsive gravitational effects and potentially violating other fundamental physical principles. Some theoretical work has explored whether quantum mechanical effects might provide the necessary exotic matter to stabilize wormholes. The Casimir effect demonstrates that quantum fluctuations can create regions of negative energy density between closely spaced conducting plates. However, the total energy remains positive and the negative energy regions are both tiny and unstable. Scaling up such effects to create macroscopic amounts of exotic matter stable enough to hold open a traversable wormhole remains far beyond any known physical mechanism. The possibility of wormholes connecting different times rather than just different places adds another layer of complexity and wonder to these theoretical constructs. A wormhole with mouths at different gravitational potentials or in relative motion could connect different moments in time as well as different locations in space. Such a temporal wormhole could theoretically allow communication or travel between past and future, opening up the same paradoxes and consistency problems associated with closed time-like curves. Recent research has explored the quantum mechanical properties of wormholes, particularly in the context of quantum entanglement and black hole physics. Some theories suggest that quantum entanglement between distant regions of space-time might create wormhole-like connections, providing a bridge between the microscopic world of quantum mechanics and the macroscopic geometry of curved space-time. These quantum wormholes would be far too small for macroscopic travel, but might play important roles in the fundamental structure of space-time at the Planck scale. The study of wormholes has also contributed to our understanding of the relationship between geometry and information in physics. The holographic principle, which suggests that all the information contained in a volume of space can be encoded on its boundary has led to new insights into how wormholes might connect distant regions of space-time through quantum entanglement rather than classical geometry. These developments hint at deep connections between gravity, quantum mechanics, and information theory that could revolutionize our understanding of the universe's fundamental structure. While wormholes remain purely theoretical, their mathematical existence in Einstein's equations continues to inspire both scientific research and popular imagination. They represent one of the most dramatic predictions of general relativity, suggesting that the universe might contain hidden pathways and secret passages that could, under the right conditions, provide access to distant realms of space and time that would otherwise remain forever beyond our reach. The grandfather paradox and self-consistency. The grandfather paradox is a gentle puzzle that emerges when we consider traveling to the past. If someone traveled back in time and prevented their grandparents from meeting, they would never be born. But if they were never born, who traveled back to prevent the meeting? Physicist Igor Novikov proposed the self-consistency principle, suggesting that the universe's laws naturally prevent paradoxes. Any attempt to change the past would be thwarted by the very structure of space-time itself, ensuring that history remains consistent. Perhaps time travelers to the past would find themselves unable to alter key events, not through any external force, but because the mathematics of causality itself guides their actions toward consistency with what has already occurred. This deceptively simple paradox strikes at the heart of our understanding of causality and free will. It presents a logical loop that seems to unravel the very foundation of cause and effect that governs our everyday experience. The paradox assumes that traveling to the past is possible and that actions taken in the past can alter the course of history. Yet it demonstrates how such alterations could lead to logical impossibilities that challenge the coherence of reality itself. The grandfather paradox serves as a thought experiment that forces us to confront fundamental questions about the nature of time, determinism, and the relationship between past, present, and future. The classical formulation of the paradox involves a time traveler who journeys back to prevent their own existence by interfering with their grandparents' meeting. But the paradox can be generalized to any situation where a time traveler attempts to alter past events in ways that would prevent their own time travel. The traveler could attempt to destroy the time machine before it's built, prevent the scientific discoveries that made time travel possible, or simply create any change in the past that would make their own journey impossible. Each scenario leads to the same logical contradiction. If the time traveler succeeds in preventing their own journey, then who or what caused the changes in the past? Novikov's self-consistency principle offers an elegant resolution to this paradox by suggesting that the laws of physics themselves would conspire to prevent any paradoxical alterations to the past. According to this principle, if time travel to the past is possible, then only self-consistent histories can occur. The universe would naturally evolve in such a way that any actions taken by time travelers would already be incorporated into the historical record they're trying to change. The time traveler wouldn't be changing the past, but fulfilling it, becoming part of a causal loop that has always existed. This principle doesn't rely on external intervention or cosmic censorship to prevent paradoxes. Instead, it suggests that the very structure of space-time and the laws of physics would guide events toward consistency. A time traveler attempting to prevent their grandparents' meeting might find themselves thwarted by a series of seemingly random but perfectly natural events. Their weapon might malfunction at a crucial moment. They might be delayed by unexpected traffic, or they might discover that their intervention actually helps bring their grandparents together rather than keeping them apart. The mathematical foundation for this principle emerges from the requirement that physical laws be consistent across all regions of space-time, including those containing closed time-like curves. If the laws of physics permit time travel to the past, they must also ensure that such travel doesn't lead to logical contradictions that would invalidate the laws themselves. The principle treats causality not as a constraint imposed from outside the physical system, but as an inherent property of the mathematical structures that describe reality. Some interpretations of the self-consistency principle suggest that free will itself might be an illusion in regions of space-time containing closed time-like curves. A time traveler might feel that they're making choices about how to interact with the past, but these choices would actually be determined by the requirement that their actions be consistent with the historical record they emerged from. Their decisions would be constrained not by external forces, but by the logical necessity of maintaining causal consistency across the entire space-time manifold. The principle also raises profound questions about the nature of information and its relationship to physical law. If a time traveler carries information back to the past, where did that information originally come from? A book could be given to a young author who grows up to write that very book, creating a causal loop where the information has no clear origin. Such scenarios suggest that information might be able to exist in closed causal loops, challenging our usual understanding of how knowledge is created and transmitted through time. Recent research in theoretical physics has explored how quantum mechanical effects might influence the operation of Novikov's principle. Quantum uncertainty could provide the mechanism by which the universe ensures self-consistency, with quantum fluctuations and probabilistic events naturally steering history toward consistent outcomes. The many possible quantum outcomes would collapse to only those possibilities that maintain causal consistency, with the time traveler's presence in the past being one of the factors that determines which quantum possibilities become reality. The self-consistency principle also connects to deeper questions about the relationship between mathematics and physical reality. If the principle is correct, it suggests that logical consistency is not just a property of our mathematical descriptions of nature, but a fundamental feature of reality itself. The universe would be required to obey not just the laws of physics, but the laws of logic, with paradoxes being prevented not by physical mechanisms, but by the very structure of existence. Quantum mechanics and many worlds in quantum mechanics. Some interpretations suggest that all possible timelines exist simultaneously in a vast multiverse. When you travel back in time, you might not be changing your own past, but creating or accessing an alternate timeline where events unfold differently. This many worlds interpretation sidesteps paradoxes elegantly. The timeline where you prevent your grandparents from meeting becomes a different branch of reality, separate from the one you originated in. You become a visitor to an alternate history, rather than a changer of your own. This interpretation transforms time travel from a paradox-ridden impossibility into a gentle journey between parallel worlds, each with its own consistent history and future possibilities. The many worlds interpretation of quantum mechanics, first proposed by Hugh Everett III in 1957, revolutionizes our understanding of reality by suggesting that every quantum measurement creates a branching of the universe into multiple parallel worlds. Each possible outcome of a quantum event occurs in a separate branch of reality, with all branches equally real but mutually inaccessible. In this framework, the universe is not a single timeline but an ever-growing tree of possibilities, with new branches sprouting at every moment as quantum events unfold throughout the cosmos. When applied to the problem of time travel, the many worlds interpretation offers a remarkably elegant solution to the grandfather paradox and all similar causal loops. Instead of creating logical contradictions, time travel would simply transport the traveler to a different branch of the multiverse, one where their actions in the past create a new history that diverges from their original timeline. The timeline they came from continues to exist unchanged in a separate branch of reality, while their actions create a new branch where events unfold differently. This interpretation transforms the time traveler from a paradox-creating agent of change into an interdimensional explorer, journeying between alternate versions of reality rather than altering their own past. In the new timeline they create, they might indeed prevent their grandparents from meeting, but this action doesn't erase their own existence because they originated in a different branch of the multiverse, where their grandparents did meet and produce the lineage that led to their birth. They become a visitor to an alternate history, a refugee from a parallel world where events unfolded differently. The mathematical structure underlying this interpretation involves the quantum mechanical concept of superposition, where quantum systems exist in multiple states simultaneously until measurement forces them to collapse into a single, definite state. In the many worlds interpretation, this collapse doesn't actually occur. Instead, the universe splits into multiple branches, with each possible measurement outcome realized in a separate branch. The observer becomes entangled with the quantum system, experiencing only one outcome, while copies of themselves in parallel branches experience all the other possibilities. Applied to macroscopic time travel scenarios, this quantum branching would occur continuously as the time traveler interacts with the past. Every quantum event influenced by their presence would create new branches of reality, rapidly generating an enormous number of parallel timelines. The time traveler would follow one particular path through this branching structure, but countless other versions of themselves would explore alternative paths in parallel, worlds where their actions had slightly different consequences. This interpretation also resolves the information paradox associated with time travel. In the traditional grandfather paradox, information seems to appear from nowhere when a time traveler brings knowledge back to the past. But in the many worlds framework, the information originates in the timeline where it was first created, and the time traveler simply carries it to a different branch of reality. The information has a clear origin and doesn't violate conservation laws because it exists in multiple copies across different branches of the multiverse. The many worlds approach to time travel also addresses questions about free will and determinism that arise in other interpretations. The time traveler maintains genuine freedom of choice because their decisions create new branches of reality rather than being constrained by the need to maintain consistency with a predetermined past. Every possible choice they might make is realized in some branch of the multiverse, ensuring that all potential outcomes are explored across the full range of parallel worlds. This interpretation suggests that time travel technology, if it existed, would function more like a device for accessing parallel universes than a method for changing the past. The destination reached by a time traveler would depend not just on when they traveled, but also on the specific quantum mechanical details of how their journey unfolded. Slight variations in the time travel process could lead to dramatically different alternate histories, with each journey exploring a different path through the vast landscape of possible worlds. The practical implications of this interpretation are both liberating and sobering. On one hand, it suggests that time travelers need not fear creating paradoxes or accidentally destroying their own timeline. Every action they take simply explores another branch of the multiverse, adding to the rich tapestry of parallel realities without erasing any existing possibilities. On the other hand, it implies that true communication with or influence over their original timeline might be impossible, as each journey to the past would create a new branch forever separated from their world of origin. Recent developments in quantum computing and quantum information theory have lent additional credibility to the many worlds interpretation, as researchers have discovered practical applications for quantum superposition and parallel processing that seem to operate according to many worlds principles. Quantum computers appear to perform calculations by exploring multiple solution paths simultaneously, much as the many worlds interpretation suggests that reality explores multiple historical paths simultaneously. The interpretation also connects time travel to contemporary research in cosmology and theoretical physics, where the concept of parallel universes has gained scientific respectability through studies of cosmic inflation, string theory, and the anthropic principle. If parallel universes already exist as a consequence of cosmic inflation or the fundamental structure of reality, then time travel that creates additional parallel timelines would simply be another mechanism for accessing the vast multiverse that may already surround us. This quantum mechanical approach to time travel transforms it from a threatening violation of causality into a gentle exploration of the infinite possibilities that quantum mechanics suggest may be the true nature of reality. Rather than changing the past, time travelers would be discovering alternate pasts that were always possible, but never explored in their original timeline. They would become cosmic archaeologists, uncovering the hidden histories that exist in the vast library of parallel worlds that quantum mechanics suggests underlies all physical reality. The arrow of time and entropy time seems to flow in only one direction, from past to future, and physics suggests this is connected to entropy, the tendency of systems to become more disordered over time. This gives time its arrow, its preferred direction of flow. In the early universe, entropy was low, and it has been increasing ever since. This increase in entropy might be what gives us our psychological sense of time's passage, our memory of past events, but not future ones. Some theories suggest that in regions of space-time, where entropy decreases, time might flow backward. These would be strange realms where effects precede causes and where aging might reverse. Though such regions remain purely theoretical, the arrow of time represents one of the deepest mysteries in physics, bridging the gap between our subjective experience of temporal flow and the mathematical descriptions of physical law. Most fundamental equations in physics are time reversible, meaning they work equally well whether time moves forward or backward. Newton's laws of motion, Maxwell's equations of electromagnetism, and even Einstein's field equations of general relativity all treat past and future symmetrically. Yet our universe clearly distinguishes between these directions, with causes preceding effects, with memories of the past but not the future, and with the inexorable progression from birth to death that defines biological existence. Entropy provides the key to understanding this asymmetry. In thermodynamics, entropy measures the degree of disorder or randomness in a system. The second law of thermodynamics states that in any isolated system, entropy either remains constant or increases over time, never decreases. This law transforms the otherwise time-symmetric equations of physics into an irreversible process that gives time its preferred direction. Hot objects cool down, gases expand to fill available space, and organized structures gradually decay into disorder. These processes all flow in the direction of increasing entropy, creating the thermodynamic arrow of time that points from past to future. The connection between entropy and time's arrow becomes even more profound when we consider the history of the universe itself. In the earliest moments following the Big Bang, the universe existed in an extraordinarily low entropy state. Matter and energy were distributed with remarkable uniformity. Gravitational potential energy was at its maximum, and the cosmic microwave background radiation had not yet been stretched and cooled by cosmic expansion. This initial low entropy condition provided the universe with vast room for entropy growth, setting the stage for the billions of years of increasing disorder that have followed. As the universe expanded and cooled, gravitational instabilities caused matter to clump together, forming stars, galaxies, and planetary systems. These processes might seem to create order from disorder, but they actually increase the total entropy of the universe by converting gravitational potential energy into heat and radiation. Stars burn their nuclear fuel, converting ordered matter into disordered energy that radiates away into space. Black holes form and eventually evaporate through Hawking radiation, contributing to the universe's inexorable march toward maximum entropy. This cosmic increase in entropy might explain why we experience time as flowing from past to future, rather than in the opposite direction. Our brains are complex information processing systems that depend on the thermodynamic arrow of time for their operation. Memory formation requires energy to create ordered structures that encode information, a process that increases entropy in the surrounding environment. We remember the past because that's the direction in which entropy was lower, allowing for the creation of ordered records of previous events. The future remains unknown because it lies in the direction of higher entropy, where the information needed to predict outcomes becomes increasingly scattered and inaccessible. The relationship between entropy and consciousness raises fascinating questions about the nature of subjective time. Some philosophers and physicists have suggested that our perception of time's passage is not a fundamental feature of reality, but rather an emergent property of how complex information processing systems like brains interact with the thermodynamic environment. From this perspective, time doesn't actually flow in any objective sense, but the increase in entropy creates the illusion of temporal passage for systems capable of forming memories and making predictions about the future. Theoretical physics has explored scenarios where entropy might decrease in certain regions of space-time, potentially causing time to flow backward in those regions. Such areas would be characterized by effects preceding their causes, with broken objects spontaneously reassembling and with heat flowing from cold objects to hot ones. In these hypothetical domains, aging might reverse, memories might fade into the future rather than the past, and the normal causal structure of reality would be inverted. While no such regions have ever been observed, they remain a theoretical possibility in certain exotic cosmological scenarios. The concept of entropy decrease becomes particularly intriguing when applied to the far future of the universe. Current cosmological models suggest that the universe will continue expanding and cooling until it reaches a state of maximum entropy known as heat death. In this final state, all available energy will be evenly distributed, no work will be possible, and the thermodynamic arrow of time will effectively cease to exist. Some speculative theories propose that quantum fluctuations might occasionally create pockets of decreased entropy, even in this maximally disordered state, potentially giving rise to new arrows of time that point in random directions throughout space. Recent research in quantum mechanics and information theory has revealed additional layers of complexity in the relationship between entropy and time. Quantum entanglement can create correlations between distant systems that seem to transcend the normal thermodynamic constraints on information flow. Some interpretations suggest that quantum mechanics might permit violations of the second law of thermodynamics on microscopic scales, though these violations would be balanced by corresponding increases in entropy elsewhere in the system. The arrow of time also connects to fundamental questions about the nature of causality and the flow of information through the universe. In regions where entropy decreases, the normal relationship between cause and effect might break down, leading to scenarios where information flows backward through time. Such situations would create challenges for our understanding of free will, determinism, and the logical structure of physical law, forcing us to reconsider basic assumptions about how reality operates at its most fundamental level. Tachyons, hypothetical faster than light. Particles tachyons are hypothetical particles that would always travel faster than light. If they exist, they would experience time differently than normal matter, potentially even traveling backward through time from our perspective. The mathematics of special relativity suggests that tachyons would have imaginary mass and would require infinite energy to slow down to light speed. They remain purely theoretical, with no experimental evidence for their existence. If tachyons could be controlled and used to carry information, they might enable communication with the past. Though this would again raise questions about causality and paradoxes, the theoretical existence of tachyons emerges from the mathematical structure of Einstein's special theory of relativity, which divides all possible particles into three categories based on their relationship to the speed of light. Ordinary matter particles, called tardions, always travel slower than light and have positive rest mass. Photons and other massless particles travel exactly at the speed of light. Tachyons would occupy the third category, always traveling faster than light and possessing what mathematicians call imaginary mass, a concept that challenges our intuitive understanding of matter and energy. The word tachyon comes from the Greek word tachys, meaning swift, and was coined by physicist Gerald Feinberg in 1967. Feinberg showed that the equations of special relativity don't actually forbid faster than light particles. They simply describe such particles as having very strange properties that set them apart from ordinary matter. While normal particles gain energy and momentum as they accelerate toward the speed of light, requiring infinite energy to reach that ultimate velocity, tachyons would lose energy as they slow down toward light speed, requiring infinite energy to decelerate to that boundary velocity. This energy relationship creates a fundamental asymmetry between tachyons and ordinary matter. Both types of particles are prevented from crossing the light speed barrier, but for opposite reasons. Normal matter cannot accelerate to light speed because doing so would require infinite energy, while tachyons cannot decelerate to light speed for the same reason. The speed of light thus serves as an impermeable boundary separating two distinct realms of existence, with ordinary matter confined to velocities below this cosmic speed limit and tachyons restricted to velocities above it. The imaginary mass of tachyons doesn't mean they would have no mass or negative mass, but rather that their mass would be described by an imaginary number when plugged into the standard relativistic equations. This mathematical peculiarity reflects the exotic nature of faster-than-light motion and suggests that tachyons would interact with space-time in fundamentally different ways than ordinary particles. Their energy and momentum would still be real quantities, but the relationship between these properties and the particle's velocity would follow patterns that have no analog in our everyday experience. From the perspective of observers moving slower than light, tachyons would exhibit the bizarre property of traveling backward through time. This temporal reversal emerges from the Lorentz transformation equations that describe how different observers measure space and time intervals. For a tachyon moving faster than light, these transformations predict that some observers would see the particle arriving at its destination before it left its starting point, creating a causal loop that violates our normal understanding of cause and effect. The possibility of backward time travel through tachyon communication has captured the imagination of physicists, exploring the foundations of causality and temporal paradoxes. If tachyons could be controlled and modulated to carry information, they might enable messages to be sent to the past, potentially allowing communication with earlier versions of ourselves or advance warning of future events. Such capabilities would immediately raise all the familiar paradoxes associated with time travel, including the possibility of preventing one's own birth or creating information, loops where knowledge appears to have no original source. Experimental searches for tachyons have consistently failed to find any evidence for their existence. Particle accelerators, cosmic ray detectors, and astronomical observations have all been used to search for signatures of faster-than-light particles, but none have been detected. Some experiments have reported anomalous results that might be interpreted as evidence for tachyonic behavior, but these have invariably been explained by more conventional physics or attributed to experimental error. The absence of experimental evidence doesn't definitively prove that tachyons don't exist, but it does suggest that if they do exist, they interact very weakly with ordinary matter. Theoretical physics has explored various mechanisms by which tachyons might be hidden from direct observation, while still playing important roles in the structure of reality. Some theories suggest that tachyons might exist in higher dimensional spaces that are inaccessible to our three-dimensional experience. Others propose that tachyons might undergo a process called spontaneous symmetry breaking, where they acquire effective mass and become confined to moving slower than light, transforming into ordinary particles in the process. The quantum field theory description of tachyons reveals additional complexities and paradoxes. Quantum tachyon fields would have negative energy densities in their ground states, potentially violating fundamental energy conditions and leading to instabilities in the vacuum itself. These instabilities might cause the tachyonic field to evolve toward a more stable configuration, possibly triggering phase transitions that could fundamentally alter the laws of physics. Such scenarios have been invoked in cosmological theories to explain phenomena like cosmic inflation and the breaking of fundamental symmetries in the early universe. Recent developments in string theory and extra-dimensional physics have renewed interest in tachyonic particles and fields. In these advanced theoretical frameworks, tachyons often appear as indicators of instability in higher dimensional spacetimes, signaling the need for the system to evolve toward a more stable configuration. Rather than representing real particles that could be observed and manipulated, these theoretical tachyons serve as mathematical tools for understanding the dynamics of complex multidimensional systems. The study of tachyons has also contributed to our understanding of the relationship between relativity and quantum mechanics, two pillars of modern physics that remain difficult to reconcile completely. Tachyonic quantum fields exhibit unusual properties that challenge standard approaches to quantum field theory, forcing physicists to develop new mathematical techniques and conceptual frameworks. These developments have deepened our understanding of both theories, while highlighting the fundamental mysteries that remain at the intersection of quantum mechanics, relativity, and our understanding of space and time. As we drift toward the end of our peaceful journey through time's mysteries, remember that you are already a time traveler. Every moment carries you forward through the temporal landscape. Every heartbeat marks another step into the future. Time surrounds you like a gentle current, flowing at its own pace, responding to gravity and motion in ways both subtle and profound. You move through it as naturally as breathing, aging microseconds faster when you climb stairs, experiencing tiny shifts in temporal flow that connect you to the cosmic dance of relativity. The universe holds pathways through time that we're only beginning to understand. Wormholes that might tunnel through space-time, particles that could carry messages to yesterday, and gravitational fields that stretch moments like warm honey in sunlight. Tonight, as you rest, time continues its quiet work. Clocks tick at their own rhythms across the cosmos, some fast, some slow, all keeping perfect time for their own locations in space. You are part of this temporal symphony, a gentle note in the universe's long song of past, present, and future. Sleep well, time traveler. Dream softly of tomorrow, and wake peacefully in your own perfect moment of now.